find the mass and center of mass of the region bounded by R in quadrant 1, where xy equals 4, x equals 1, x equals 4, and y equals 0. The density of a function, rho of xy, is equal to k times x squared. Let's begin with a graph of the region. If we're looking at the equation xy equals 4, you could solve this for y to get y equals 4 over x. When you sketch this in quadrant 1, this, when x is equal to 1, y is equal to 4. When x is equal to 4, y is equal to 1. The rational function, so it's got those asymptotes. X equals 1 is the vertical line through 1 on the x-axis. X equals 4 is the vertical line through 4 on the x-axis. And y equals 0 is the x-axis. So you can see the region that's bounded by those equations here. And we want to find the mass and center of mass of that region. So we're going to end up setting up 3 double integrals, one for mass, one for the moment with respect to the x-axis, and one for the moment with respect to the y-axis. For all of those double integrals, we want to determine the bounds of integration, and we can do that by using a representative rectangle. And if we draw out a vertical rectangle, since it is a vertically simple region, then this differential area here can be found by multiplying dy times dx. So that's going to help us with the order of our differentials, as well as determining the bounds of integration. We want to find the bounds for y. So we want to look at the bottom of that rectangle. What does y equal? Y equals 0 on the bottom of that rectangle. We want to look at the top of that rectangle. The top of that rectangle is this line, which is y is equal to, this graph, which is y equals 4 over x. That's going to be our top or upper bound for y. And then if you determine your bounds for x, you slide that rectangle all the way to the left. This region is x equals 1. And then slide it all the way to the right of that region, and the right x is equal to 4. So your lower bound for x is 1, your upper bound for x is 4. So now our formulas here for mass to begin with. Mass is equal to a double integral r of the density, rho of xy, times the differential area. And if we plug in, let's determine our bounds of integration here. We get the integral of the double integral of the density, which is k times x squared. The differential area is dy dx. The inside bounds are for y, which go from 0 to 4 over x, and the outside bounds are for x, which goes from 1 to 4. Now, I won't go through the steps of evaluating this integral. We've practiced this quite a few times, evaluating integrals. I do want to point out that this k is a constant. You can bring that out in front, evaluate it, and get the answer to this would be 30k. So the mass of that shaded region is 30k. Now let's find the moment with respect to the x-axis, and that is also a double integral of the distance from the x-axis, which is y, times the density times your differential area. So when we set up this double integral, our bounds are going to be the same. The integral from 1 to 4, or the integral from 0 to 4 over x. The only difference is that we're going to have that y in the integral. So it's going to be y times kx squared times dy dx. Again, if you work through that, you can bring that constant out in front. You integrate the inside with respect to y, evaluate it, and then you get a single integral, and you'll work that out to be 24k. The last integral that we need to set up is the moment with respect to the y-axis. That's going to be a double integral r of the distance from the y-axis, which is x, times your density, rho of xy, times your differential area. So this ends up being, again, the same bounds of integration from 1 to 4, from 0 to 4 over x. The only difference here is that we have that x times the density, so it's going to be x times kx squared dy dx. And then again, if you work through that, work it out, you get 84k is the moment with respect to the y-axis. We're going to put this all together to find the center of mass, where we take the moment with respect to the y-axis divided by the mass, and the moment with respect to the x-axis, divide that by the mass. And we're going to get moment with respect to y, which is 84k divided by 30k, and those k's are going to simplify, divide out, and 24k divided by 30k. And then when we simplify that, we can write our answer as a decimal here. 2.8 comma 0.8 is the center of mass, and you can check to see if that is indeed somewhere on the mass itself by locating the point with coordinates about 2.8 up 0.8, so it's about right there as your center of mass.